Thank you.
Hello everyone. In this presentation, I'm going to talk about a multidisciplinary optimal design of an active control system and state estimator for an aircraft. This work was done by Christopher, Stephen Greer, and Yousef Sardahi from Marshall University. So this is my outline. So I'll start with objective introduction, the methodology that we followed in this work, and then I'll introduce the result. And some of the concluding remarks. So the objectives, we want to design an active control system and also estimator or observer for an aircraft wing with the 3 control surfaces in a multidisciplinary and a multi-objective optimization. The second objective, we want to investigate the effect of the airstream velocity on the solution of the optimization problem. Now, multidisciplinary optimization has received a lot of attention recently because of its great impact on the performance of aircraft wing. Now, when we do a control system design, usually the control system design involves multiple and often conflicting goals. So this is why the optimization should be handled in a multi-objective settings. And for multidisciplinary, we need to include some of the design parameters of the control system. In our case, also the estimator, in addition to the combination of structural and aerodynamic parameters of the aircraft wing. For design parameter, for design purposes, we are going to need a model. So here, this is the matrix differential equation that describes the or that predicts the performance of the aircraft wing with 3 control surfaces, 1, 2, and 3. This is the definition of all the parameters in this matrix differential equation. For control purposes, we take this matrix differential equation, we convert it into state space. We convert it into state space, the EBCD model of the system that we will be using in the control system design. We design a full state feedback, assuming that we have access to a state of the system. U of t here is the control signal, which is nothing but the deflection of the 3 control surfaces. So U of t is a vector that contains B1, B2, and B3, the deflection of the 3 control surfaces, as we mentioned. KC is designed by using LQR, linear quadratic equator, that has 2 objectives inside. The first one is the state energy. This one is the control energy. We can notice that the state feedback matrix is a function of R and also P. P is also a function of Q and R. So these 2 matrices play a very important role in the value of KC. We do not have access to all of the states of the system. This is why we need to design an estimator, which is a copy of the system, of the state space system, except that we assume that we do not know the dynamics of the aerodynamic, the dynamics of the gust load in this case. So it's a copy. We add to it L, which is the estimator gain multiplied by the error between the 2 states and the estimated one. So I had here indicates the estimated state of the system. Okay. The design objective, we have 4. We want to maximize the stability robustness of the system. We want our system to be able to reject external disturbances such as aerodynamic loads. We want the system to use a small energy, and at the same time, we want the estimator energy to be small. And even though the estimator energy comes at no cost because it's nothing but a computer algorithm, if the value of L is very large, that might amplify some of the noise components, right? And this is why we need the Frobenius norm of this estimator energy or the estimator gain to be small. The design parameters, it's a multidisciplinary design, so it includes the control design parameters Q1 to Q8 and from R1 to R3, in addition to the small r, which actually describes how fast is the estimator with respect to the closed loop dynamic, in addition to some of the structural and aerodynamic parameters of the aircraft wing, such as alpha 1, alpha 2, and EC. Alpha 1 size S1, alpha 2 we use it to size S2, okay, and EC tune the chord length of the control surfaces. So this is a multidisciplinary design. So we have the design objective, the design parameter, we specify the constraints. More information about the constraints you can find them in the paper. We solve the optimization problem by using non-dominated sorting genetic algorithm, and these are the settings of the algorithm. This is one of the popular algorithm that researchers use in a multi-objective optimization. We solve a multi-objective optimization. We get the Pareto set and Pareto front. Pareto front is the function evaluation of the Pareto set, and these curves justify why the optimization was done in a multi-objective settings. You can notice that there is a conflict between the control energy and also the stability robustness of the system, between the estimated energy and the stability robustness, and also between the control energy and the ability of the system to reject external disturbances, and also between the estimator gain and the ability of the system to reject external disturbances. How this response of the closed system looks like at different stability robustness values. This is how the estimator and the closed loop system, the estimator in the blue curve, the closed loop system in the red curve, looks like when lambda c equal -10 and when lambda c equal -31. At lambda c max equal -31, it's better because the stability robustness is high, the control energy is high, and also the estimator gain in this case is high. So the estimation here is better, even though the estimator assumes that you do not know the dynamics of the gust load. We also investigate the impact of the airstream velocity on the dominant ball of the closed loop system and also the dominant ball of the estimator. For the estimator, I mean, it's always stable regardless of the airstream velocity, okay? Even if you increase it to up to 1,000 meters per second. For the closed loop system, it will become unstable at certain values. For example, at lambda c equal -10, it crosses the imaginary axis at about 218 meters per second. And at lambda c max equal -31, it crosses the imaginary axis at 238. But in all cases, the flutter boundaries is extended by more than by at least 69%. Now, in active aerostatic control, the flutter should be at least 15% or more. So our design actually satisfies that. Okay, so we have studied the multidisciplinary and multi-objective optimization of aircraft wing with the 3 control surfaces. We have 15 design parameters and 4 objectives that were, and the optimization problem was solved by non-dominated self-genetic algorithm. The optimization was multidisciplinary. We have 3 parameters related to the span-wise and the coordinate of the control surfaces, and about 11 other parameters related to the LQR, and 1 parameter to place the estimator balls to the left of those of the closed loop system. 4 objectives are included: minimization of the control system response to the gust load, maximization of the closed loop stability robustness, minimization of the control energy, utilization and minimization of the Frobenius norm. We obtained both of the Pareto set and the Pareto front of the system of the optimization problem. The balls of the closed loop system are observed for gains versus airspeed or airspeed velocity for different level of relative stability. Show that the flutter boundary can be extended by at least 69% when lambda c max was about -10. This work was supported by NASA through this grant. Okay, this is the grant number. Thank you very much for your listening, and if you have a question, please let me know. Thank you.